Hello and welcome back. We are now about to embark upon a much foreshadowed lecture. Is that the right word? A lecture that I've teased several times. I've talked about the collapse of the calculus. I talked about infinitesimal calculus, and the mathematicians were just fine in saying, hey, if it works, it works. And it worked until it didn't. Dum, dum, dum. Well, we're finally there. Finally going to hear the story of this part. Now, to understand what's going on here, and this story takes place in like the middle of the 1800s, 1850s, 1860s till late that time, up through like the 1880s, let's say. It's pretty contemporaneous with actually the development of non-Euclidean geometry that we covered in the last couple lectures. So to understand what's going on here, let's go back and take a look at our infinitesimal calculus again. Remind ourselves how that works. All right, so let's say we're gonna drop a rock, and after t seconds, we're gonna say the rock falls t squared feet. Okay, and I know it's supposed to be 32 t squared, but this is just easier. So we'll say how fast is it traveling at 1 second. Now, remember, speed is the change in distance over the change in time. These little triangles here are the Greek letter delta, and that's the symbol that mathematicians use for change. All right. Now, exactly at 1 second, the rock doesn't travel any distance, and it doesn't travel any time. So that gets us a zero change in distance over zero time, which is bad. In mathematics, you never want to divide by zero. So we've got to do a different method to it. And what Newton said is, let's take a look between 1 second and an infinitesimal amount after 1 second. I'm going to go 1 plus, and let's say delta t. Delta t now for the change in time, but we're going to let that be infinitesimal. Okay? At 1 second, it has fallen. It is at a location of 1 squared feet. At 1 plus t seconds, or 1 plus delta t seconds, it's 1 plus delta t squared feet. So if the speed is the change in distance, change in distance over the change in time, that's going to be our ending time, our ending distance, 1 plus delta t squared, minus our starting distance, 1 squared, over our change in time. Now here's the thing. If we plug in 0 for our change in time here, if we let delta t equal to 0, we get 1 squared minus 1 squared over 0, which is basically 0 over 0. So that's when we talk about at the exact 1 instant, there's no time changing, we get a 0 over 0. So we cannot let that delta t be equal to 0. But if we do some algebra first, so now we've got 1 plus delta t squared. Well, whenever we square something, that means we're multiplying it by itself. And if we go through FOIL, that's firsts, outers, inners, and lasts. And that's going to get us, for 1 plus delta t squared, 1 plus 2 delta t plus delta t squared. And we subtract from it 1 squared right here is just 1 again, all over delta t. And the thing is this, these 1's in the top cancel. And we're left with 2 delta t plus delta t squared over delta t. Now we have a delta t common to both terms in the top, so we can factor it out. So we just have 2 plus delta t times delta t. We factored a delta t out of 2 delta t and a delta t out of delta t squared. And here's the thing. Now we can cancel the delta t's in the top and the bottom. And by canceling those out, it is now safe to plug in 0 for delta t. We can make it 2 plus 0, which is 2. All right. Now, as I have said, this works. And, some philosopher types or whatever maybe had some problems with this. Well, what is delta t? At one point, you can't assume it's 0, but in the end, you do assume it's 0 to solve it. Is it 0 or is it not 0? This is contradictory. Or Berkeley ridiculed this all as delta t must be a ghost of a departed quantity and so forth. But it worked. Now, it worked for a long time, a couple hundred years. Here's the problem. The problem is when you get into multivariable calculus, if you've got equations with, let's say, an x and a y in it, because now you're going to have two infinitesimal quantities, a delta x and a delta y, the infinitesimal increment on x and an infinitesimal increment on y. And our whole strategy here is to not plug in 0 until we've done an algebraic manipulation to make it safe to plug in 0, and then we plug in 0. But we could manipulate our equation algebraically to make it safe to plug in 0 for delta x, and then manipulate it a little more to make it safe to plug in 0 for delta y. Or we could manipulate it algebraically to first make it safe to plug in 0 for delta y, and then manipulate it algebraically to make it safe to plug in delta 0 for delta x. And the thing is this, for some functions, depending on what order you do that in, you get different answers. And there's no reason you should. You know, mathematicians going over this, they're like, I do it this way, I get one answer. I do it this way, I get the other. There's no real reason to choose between the two ways of doing it. How do you know which is the right answer? You don't even have any reason to believe either of them's the right answer. Remember my story about the burning of the Library of Alexandria? And I said, the more answers you have, the less you're likely to believe any one of them. How do you know either of them's right? And mathematicians didn't know what to do. This was a real problem. Suddenly, if it works, it works, stopped working. And what did mathematicians do? Well, they did what a lot of people do in a time of crisis. They got religion fast. And by that, I mean they went back to that good old time Greek rigor. This is the start of that period I've called the shotgun wedding between math and philosophy, when all of a sudden mathematicians said, wait. What have you philosophers been saying all this time? What exactly do you think is wrong with what we're doing? How exactly might we be able to fix this? And so whereas we were in a big phase of if it works, it works. Now all of a sudden we are shifting into a phase of rigor, not because of philosophical concerns, not because of just wanting to be rigorous, but because it stopped working and we got to figure out why it's not working and make it work again. So now, in fairness, ever since Newton introduced infinitesimals, mathematicians haven't taken them necessarily seriously. They say, this is really just a manner of talking. By infinitesimal, we really mean it's just a very small number, or maybe a number that's getting smaller and smaller all the time. And it's this second idea. It's a quantity that's getting smaller and smaller all the time, which is what they're going to latch onto. They need to now make this notion rigorous up to at least the standards of old Greek rigor, and then see if that solves their problem. Well, let's take a look at this notion of getting smaller and smaller all the time. Whoops, that's not what I wanted to do. I wanted to share my screen. There we go. All right, we're gonna need a new whiteboard here. All right, so what we had in our previous thing was we had this 2 plus delta t, and our move was to basically get 2 plus delta t to be equal to 2. Now, here plugging in 0 for delta t is unproblematic, and that's fine. But this is exactly the step where things kind of blow up when we're dealing in multivariable calculus. Now, multivariable calculus is where the problems occur, but single variable, when you're only dealing with one variable, an x or a t, is so much easier. So we're really going to do all of our rigor here in the single variable world, even though it might appear that plugging in 0 would be easier, it would work. Yeah, fine, but we're developing the process which is going to save us in the multivariable world. All right, so what is going to be this step? Let's take a look at what 2 plus delta t moving to 2 looks like on the number line. So here's 1, here's 2, here's 3. So like, let's say here, 2.5 is where our point is when delta t is 0.5. When delta t is 0.5, we're at 2.5. When delta t is 0.25, we're right here at 2.25. And as we make delta t smaller and smaller, it moves like this. Now, this picture might look a little familiar. This is the paradox of Elia to Zeno. Remember way back with the Greeks, we started, Zeno is traveling from Elia to Athens, is what I meant to say. Elia to Athens, and we were trying to figure out how many points does he pass through in order to get to Athens. This is exactly the same process that the mathematicians are now struggling with, struggling to solve, to explain, to do rigorously in their calculus. So they finally, it's time to pay the piper. They finally have to face this paradox and figure out a solution to it in order to save the calculus. All right, so what do they do? Now, to explain what they did, I'm gonna go back and take a look at the assumptions that lie at the base when I cashed out this paradox at the start. Way back when we had some Pythagorean assumptions, if you recall that. So what are some Pythagorean assumptions? I set them up in order to lead us to our paradoxes. So the first was space is made up of points and time is made up of instances. Second is you can only cross a finite number of points in a finite time. The third is things can either be moving or stationary, but not both at the same time. And the last is every 2 points have a unique midpoint. So those all statements seem to be unproblematic, but they led us through Zeno's paradoxes to problems. Okay, what mathematicians are going to do is this. They're going to reject that second premise. They're going to reject that you can only cross a finite number of points in a finite time. And this is going to open up a whole can of worms. They're going to say, you know what, we're going to think infinite processes are okay. We're going to allow them. Now, the thing is, allowing infinite processes causes a lot of problems. There's a lot of difficulty when you're trying to do calculations with infinities. And the Pythagoreans knew it, and that's why they hated it. And that's why they said infinite processes were irrational. That's where we get the notion of an irrational number from, because it's an infinite decimal expanding going on. And they avoided it totally. But let's remember what's happening in mathematics at this point in time. Mathematicians just entertained the idea that the fifth parallel postulate might be wrong, and you could deny it. And they developed a whole new geometry out of that. Weird geometry, but it seemed okay. In that way, they sort of resolved a difficulty that had been plaguing mathematicians for over 2 millennia. And maybe now is the time to finally tackle all of these difficulties with infinity that the Greeks were aware of and have been keeping mathematicians sort of shying away from infinities for all these millennia. Maybe now's the time. And so mathematicians took the bull by the horn. They said, we're going to allow infinite processes. They took a look at all of the problems that this caused up, and they went ahead and they created a solid, rigorous theory that made it all okay. They were able to overcome it. So just like they were able to develop a non-Euclidean geometry, they were able to develop the mathematics of infinite processes. So let's take a look here. How did they do it? What is the foundation of their solution? All right. Oops, we could go with this one. So let's take a look at this Elliot at Athens. How exactly are we to understand this infinite process? Well, let's call this distance here 1 EA unit, 1 Elliot at Athens unit. We'll say it is 1. At this first point here, Zeno is half of the way there. At this point here, Zeno is 3/4 of the way there. At this point here, Zeno is 7/8 of the way there, and then 15/16 and so on. So if we want to take a look at how much of the way there Zeno is, we've got a half, 3/4, 7/8, 15/16, and so on. Now, notice in each of these fractions, the numerator, the top, is only 1 less than the denominator. Now, if the numerator and denominator were the same, that would be 1. So this is really 1/2 off of 1. And this is a 4th off of 1. And this is an 1/8 off of 1. And this is a 16th off of 1. We're getting closer and closer to 1 EA unit. What we're going to do in this case is we're going to say that Athens is the limit of this journey. It is the limit of this process. Now, how are mathematicians going to define limits? Remember, in Greek rigor, Greek geometry, everything is defined. Everything is either a core definition defined off of previous terms, all that kind of stuff. How are we going to define limits? The idea is this. So we're going to say that Athens is the limit of this process if you and I play a game and I can always win the game. And here's the game. You name some tolerance, like 1/32 of the distance from Elea to Athens. And I will name some number of steps such that after that many steps, Zeno will always be within that tolerance of Athens. So you say, I want to be within 1/32 of Elea to Athens distance. I reply with 5 steps. All right, so let's take a look at what 5 steps look like. The first step is a half, the second is a fourth, the third is an eighth, each one is half the previous one, the fourth is a 16th, and the fifth is 1/32. Oops, 32nd. At 5 steps, I am within your tolerance, and everything after that, 1/64, etc., is going to be closer than 1/32. So you give me a tolerance, 1/32. I will give you some number of steps, like 5, such that for there and everything after there, Zeno is within your tolerance of Athens. You could give me a tolerance of like 1/100. What I would do is I would say, let's say, 7 steps. So let's take a look. First step was a half, second step was a fourth, third step was an eighth, fourth step was a 16th, fifth, there's our 1/32, sixth is 1/64, and the seventh is 1/28. Now 1/28, notice we passed up 1/100. 1/28 is smaller than 1/100. So at the 7th step, we are within 1/100th of the distance from Elea to Athens, and every step thereafter, we're going to be within that distance. If I can always win this game, no matter what tolerance you give me, I can name some number of steps such that after that many steps, Zeno will always be within that distance of Elea, no matter how small a tolerance you give me. That's what it means to say that Athens is the limit of Zeno's journey. So to write this in sort of some mathematical terms, we're going to say the limit as the number of steps goes to infinity of a sub n, and this is going to be like our location at n steps, is, we'll use L for the limit, if for all, and we'll say T for tolerance, for all T that you give me, there is an n, that's number of steps, such that for all steps after that, all little n bigger than n, the distance between our step location and that limit point is less than the tolerance. And this here is the definition of a limit, the rigorous definition of a limit. And this ends up being the foundation, the groundwork, the rigorous definition on which mathematicians are able to recover, replace, even sometimes calculus. This is now the limit theory of calculus. All right. Now we kind of understand. So what a mathematician would do is this. Let's go back to Elea and Athens. Mathematician would reject the second premise. You can only travel through finitely many steps in a finite time. Admit that we're going to allow infinite processes. That has a challenge of, well, you need to tell me how I have to deal with infinite processes. And here is the first step on dealing with that challenge. We're going to come up with a definition of a limit of an infinite set of processes. There we are. That deals with from Elea to Athens. What that leaves us with is good old Achilles and the tortoise. So we solved the paradox of the arrow by at the very beginning, our first shot at infinitesimal calculus, how we recognize that we have 0 over 0 is bad, so we want to throw in a little infinitesimal amount. That solves the paradox of the arrow. This definition of limit now solves our paradox of from Elea to Athens. Now what's left is Achilles and the tortoise. So Achilles is racing the tortoise, if you recall. And let's say, for the sake of argument, that Achilles travels twice as fast as the tortoise. And let's say he gives the tortoise a 1 head start. I don't know, let's say 1 mile. Does that sound reasonable? I just want simple numbers. 1 head start. All right. They go, and Achilles covers that distance. And since Achilles travels twice as fast as the tortoise, and the time it takes Achilles to cover that 1 distance, the tortoise travels a half a distance. All right. So then Achilles covers that distance. Boom, 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 a half here. But in time it takes Achilles to cover that distance, the tortoise covers half of that. So a quarter distance. All right, Achilles covers that, a quarter. And at the time it takes Achilles to cover the quarter distance, the tortoise covers 1/8 of the distance, 1/8 of a mile, let's say, and so on and so forth. So where does Achilles pass the tortoise? Well, we have to add up now infinitely many numbers. 1 plus a half, plus a fourth, plus an eighth, plus a 16th, plus a 32nd, and so on. We need to now develop a math for adding together infinitely many numbers. What is that sum? And you thought regular math was hard to do without a calculator. Try adding together infinitely many numbers. And let me tell you, you can't use a calculator for that. So, as it turns out, we have the tools to do this. What we need to do is just reduce this to the previous problem. Now, if you take a look up here at the beginning again, here's Achilles and there's the tortoise. We can ask ourselves not how much distance did Achilles cover, but where is Achilles? Here he is after the first leg of his journey, he's 1 mile into this race, this marathon. After the second leg of his journey, he's 1.5 or 3/2 a mile into his journey. After this third leg, he's, I'm losing space here. This is 7/4 of a mile into the journey and so on. And so what we have here is this notion. We got 1, our first leg is 1. Our second leg of the journey is 1 plus a half miles long, which is 3/2 of a mile. The third leg of our journey is 1 plus a half plus a fourth, which is 7/8 of a mile long, and so on and so forth. Now what we're doing here is we're converting our sum into a sequence of terms. 1, 3/2, 7/8. Now that's going to become, 7/4, I'm sorry. 7/4. Now that's going to become 15/8. So if I can do this in my head, 31/16, and so. And now what we do is we apply our definition of limit of a sequence of terms from the previous slide to this one to figure out where Achilles passes up the tortoise, where Achilles meets the tortoise. Now let's take a look here. If you notice the top, the numerator is almost twice the denominator, the bottom. So the numerator is 1 less than twice the bottom. So it would seem like it's getting closer and closer to 2, twice the top, twice the bottom. At this first step, we're 1 away from 2. So this column, this row here is how far away from 2 we are. And here we're 1/2 away from 2. And here we're 1/4 of a mile away from 2. And here we're 1/8 of a mile away from 2. And here we're 1/16 of a mile away from 2, and so on. So we can see we're getting closer and closer to 2. So let's play this game. I'm going to speculate that Achilles passes the tortoise at 2 miles. You give me a tolerance, like let's say 1/32, and I will give you a number of legs of this journey. I will say 5. This is now just like the previous problem. Or actually, we have to do 6 now because we're starting with 1. So this is our first leg, our second leg, our third leg, our fourth leg, our fifth leg. And now at the 6th leg, we are 1/32 away from 2. You give me a tolerance of 1/100th of a mile, and we'll go 2 more. So that's 1/64 is the 7th leg of our journey, and 1/128 is the 8th leg of our journey. And now we're within 1/128th of a mile from 2, and so on and so forth. So this sequence of spots is limiting to 2. So 2 is the limit because I can always win this game. You give me a tolerance, and I can give you back a number of steps such that Achilles is within that number of steps. 2 is the limit. So this solves Achilles and the tortoise. The basis of it is we have to add up infinitely many numbers. The way we do it is we convert it to an infinite sequence of terms, the partial sums of the first so many terms. And then we look at that sequence and we use the work on our previous slide to figure out where that sequence converges to. All right. So, now, it might not be obvious how we, for example, use this limit process and this definition of limit and these techniques to actually calculate things. I mean, how do we use it in math? But recall I was giving you everything in one dimension where we really theoretically could just plug in 0 for the delta t. It's these things which form the basis of our study of what's going on in multivariable calculus, which starts solving these problems. So that's where everything starts to actually work. And now we have a class called multivariable calculus, and it is considered a successful class, and you're learning stuff in it because we have these limit processes that fixed up what I call the collapse of the calculus and made it work again. Now, the thing is this. What mathematicians are now allowing is they have now, just like we created a new non-Euclidean geometry, a geometry the likes of which we had never seen before in millennia of mathematics, now we have a new mathematics, a mathematics of infinite processes. And this was mainly developed in, say, like the 1870s and 1880s. Well, it's not long before mathematicians start asking the question, what's next? Now that we can complete an infinite process, what's the next thing we can do? Where can we go from there? Could we do an infinite sequence of infinite processes, an infinite sequence of an infinite sequence of infinite processes? Where does it end? Well, let's keep on going. And that route, that avenue, that of exploration, of pushing the envelope beyond even this accomplishment we just did, leads to a new answer to an old question, what's first? Remember, way back when, Pythagoreans said everything is number. Everything, all mathematics was founded on number. And then because that was problematic, they said, well, everything is geometry. Numbers are just line segments and such. Eventually, Kant said everything is a manifold of intuition of our space and time in our minds, all right? Fine. Well, this process that we're going to look at in the next video, what's next, is going to leave us a new answer to the question, what's first in mathematics? And the new answer will be set theory. That is, everything is sets. We've gone from everything is number, everything is sets. So this is what we're covering in the next video. Transfinite, beyond finite arithmetic, which leads to set theory, which becomes a new answer to the old question, what is mathematics about? I look forward to seeing you there.